The intuition behind the Schwarzschild radius is the following. Let's consider for simplicity a planet which is orbiting around another planet with mass capital M, and we will consider this to be the Sun, and this planet is orbiting around the Sun. The Schwarzschild radius is the radius at which the gravitational energy is equal to the maximum kinetic energy that the body, and in this case the planet here with mass lowercase m, can have. In particular, if we consider the kinetic energy, we can simply write 1/2 the mass of the body times the velocity squared, and we will consider the speed of light squared, so c will be the speed of light. A body with a non-zero mass will never reach exactly the speed of light, so we are reasoning in the limit for very large energies, so the energy should be very large in order for this non-zero mass to reach the speed of light. This is to give intuition, and this kinetic energy will equal the potential energy given by the gravitational constant g times the two masses, m times lowercase m, divided by, in this case, here we have the Schwarzschild radius, which is the minimum distance here. So this will be the greatest potential energy, and here we have the largest kinetic energy. And the speed here, in general, will be the escape velocity that this body will have in order to escape from the Sun. And here, if you solve this equation, you will get Rs equal to 2gm divided by c squared. And this is exactly the Schwarzschild radius. Now, since the mass lowercase m does not appear in the formula for Rs, the Schwarzschild radius, we deduce that we can apply the formula to massless bodies as well, light, for instance. And this agrees with the fact that light cannot escape from black holes. When analyzing or studying the relativistic effects on planetary orbits, we already found that the potential energy contained a correction, a relativistic correction. So let me rewrite the formula for the potential energy that we derived. In particular, it's 1/2 L squared divided by mr squared, where L is the angular momentum of the system. And in this case, here the system is composed by these two quote-unquote particles, these two bodies. One is this particle, which is actually the Sun. For simplicity, we can assume that the only body which is moving is this planet here. It means that this is actually the angular momentum of the planet with mass m. Then we have minus g mm over r, and this is the usual potential energy that we also have in non-relativistic physics. And then we have a correction term, which is given by minus L squared g m divided by m r cubed c squared. And this is due to relativistic corrections. So this is a relativistic correction, and it's due to the theory of relativity. In non-relativistic physics, there can exist arbitrarily small orbits with arbitrarily small angular momentum L. But in general relativity, this is not so. It's not possible. Because if you take the derivative of the potential energy with respect to r and you set it equal to 0, you will find r equal to L squared c squared plus or minus the square root of L to the fourth c to the fourth minus 12 L squared g squared m squared lowercase m squared c squared, like this, and then we have to divide this by 2g capital M lowercase m squared c squared. And from this expression one can actually understand that if the angular momentum L is less than the square root of 12 times mg capital M divided by c, then this square root here will become imaginary. And it means that stable orbits do not exist anymore. So this is important because you can see that in general relativity, at some point, if the angular momentum is too small, we don't have stable orbits anymore. And stable orbits can be found by setting the derivative of the potential energy with respect to r equal to 0. Now for L equal to this value here, so if L is exactly equal to the square root of 12 mg m over c, then from this expression here you can also find r equal to 6 gm over c squared, which is equal to 3 times the Schwarzschild radius. And in this case it means that this square root here is equal to 0. So you only have one solution, only one value for r, because in general if L is large enough, you have two solutions, so you have two radii. Now it means that there are no stable orbits with a radius which is smaller than 3rs. And on the other hand, for orbits of massless particles like light, let's consider the formula for the potential energy. So this is rigorously true if we have a planet, in this case orbiting the Sun, and this planet has a non-zero mass. Now let's try to think what could happen if we let this mass here go to 0. And in the end we want to find something useful for light, a useful description of what happens when we consider light, because in general this is not true if we consider light. But we can do some kind of a stretch of the imagination. So let's use some kind of imagination and understand what's going to happen here. So if the mass m is very small, this term here can be neglected. It means that the potential energy will be approximately equal to 1/2 L squared divided by m r squared, and then we have minus L squared gm divided by m r cubed c squared. We will let m go to 0. So we are already thinking that m is a small value. And of course, in this case, we have to make sense of this expression, because when we divide by something very small, well, we might get something very large. We cannot really divide by 0. But before doing that, now let's take the derivative of the potential energy with respect to r and set it equal to 0. If you do that, and you do this simple calculation, what you get is something that does not depend on the mass m. And in particular, you get r equal to 3gm divided by c squared. And this is exactly equal to 1.5, the Schwarzschild radius. So in this case, for light, you get something different from before. So it means that light has a different critical radius. This is like a critical radius. This means that light cannot orbit around the mass with a radius which is smaller than a radius equal to 1.5 times the Schwarzschild radius. But it is still smaller than 3 times the Schwarzschild radius, and that is the limit for objects with a mass, and in this case we were considering planets.